Secondly, on the behalf of our department and all the attendees, I would also like to thank Dr. Dheeraj sir for organizing this session. So I hope you all are familiar with our today's session and the title of our today's session, that is Fundamentals of Physics. Before directly jumping onto the discussion, I just want to make sure that we all have enough motivation to move forward with this topic. So let me just take a few minutes of you all. So we live in a world which is driven by technological advancements, and oftentimes we overlook the underlying science governing these advancements. But the truth is that only after understanding the fundamentals, scientific discoveries as well as technologies become more relevant, as well as exciting. So it is of paramount importance to discuss the fundamentals as they are the building blocks of great inventions and discoveries. The journey of physics has been one of humanity's most intellectual pursuits, which led to evolutionary ideas like that of Sir Isaac Newton's, which unified gravity. That is, it brought together the understanding of observable phenomena of gravity on Earth with observable behavior of celestial bodies in space. Then, with the advent of 19th century, it brought new revelations with thermodynamics and study of energy transformations. Concurrently, James Clerk Maxwell famously unified electricity and magnetism, which paved the way for technologies such as radio and modern telecommunication. Then 20th century witnessed a paradigm shift with quantum mechanics and Einstein's theory of relativity. Quantum mechanics forms the basis of quantum computing, which may bring significant changes in our lives in the future. And relativity is not a thing of physics textbooks only, as it finds great applications such as in global positioning systems, etc. So, at its core, physics is founded on fundamental principles that I just mentioned, and these principles govern all the phenomena regardless of scale or context. There is this one great idea that I think we all should live by, and I really like, and it goes like the brilliance of advanced techniques shines brightest only when built upon a deep understanding of the fundamentals. Actually, it's the basics that elevate true mastery. So, keeping this in mind, I think today's discussion is going to be of paramount importance actually to all of us, as we have one of the great researchers, Dr. Govind Krishnaswamy, to discuss about fundamentals of physics. Dr. Krishnaswamy is a professor of physics at Chennai Mathematical Institute, India. He has done his bachelor's of science in physics and bachelor's of arts in mathematics from University of Rochester, New York, USA. Then he moved on to do his master's in science from the same university and did his PhD in theoretical physics from University of Rochester again. So Dr. Krishnaswamy is a recipient of multiple reputed fellowships. To name a few, he was a Marie Curie Fellow at Spinoza Institute and Institute of Theoretical Physics, Utrecht University, Netherlands. He has also held a position as EPSRC Fellow at a Department of Mathematical Sciences and Center for Particle Theory, Durham University, UK. He has also been a Ramanujan Fellow at CMI, India. Dr. Krishnaswamy has been awarded multiple awards and grants. His interest majorly lies in theoretical and mathematical physics, including quantum field theory, particle physics, fluid dynamics, plasma dynamics, nonlinear dynamics, and integrable systems. Actually, Dr. Krishnaswamy has achieved so many academic milestones that the list still hasn't come to an end. And I'm sure, like me, we all have this dream that we can publish a book someday. And Dr. Krishnaswamy has done this. So he has written a 750 pages voluminous book titled Classical Mechanics from Particles to Continua and Regularity to Chaos. This book has been published by Hindustan Book Agency, and global print and online editions are published by Springer Nature. This book is a self contained treatment of classical mechanics that emphasizes the wider connection of this subject to other branches of physics, such as quantum mechanics, thermal physics, electromagnetism, optics, etc. The book is going to be, oh, okay. So, as physics students, I'm sure that this book is going to be extremely useful to all of us. Now, I just want to mention one important thing, sir, and it is that we have had already asked our participants to participants to post the questions via a link that we had given. So, on the behalf of the attendees, Vanshika, Sanskriti, and Anshika, they'll be asking the questions. So, without further ado, over to you, Megha. Thank you.
Okay, so without wasting any time, so let's start with our first session of questions. So over to you, Vanshika, Sanskriti, and Anshika. Sanskriti,
Okay, so
Anshika, and Vanshika.
yes, good evening, sir. Sir, I would
Hello,
like to ask
good
the first.
evening.
Good evening, sir. Should I start or you want to say something?
Uh, sure, I would first, of course, like to thank all of you for joining and for inviting me for this program, and especially to Dr. Dheeraj for suggesting this. Um, I really appreciate the effort you have put into this. Let's continue. I've, of course, not heard, I don't know too much about Punjab University, but I know it's one of the very old universities in India and moved over from Lahore, I think, long ago. Um, and I've met some people from there, but and I've read a little bit of their history, but I have forgotten some of it now. But it's very interesting. But please, you go ahead. We'll talk more about other things later.
Sure, sir.
Yeah,
So
there's a nice
first
article.
question.
But before you
Uh-huh.
go there, so I believe there was a professor, or perhaps he's emeritus now, Arun Kumar Grover at your department, and he's written a very nice account of the history of physics in I think it's called Northwestern India or something like that. It's a really very interesting, not just physics, it's all of science, and centered around, of course, Punjab University. Please go ahead.
Okay, sir. So first question is from Mega herself. Like, what is spin? We were told that it is clockwise and anti-clockwise, but that's not so. Then how can we visualize it?
Okay. Well, yes. Okay, so let's start in classical physics. Spin is, yeah, like a top or a rigid body. It can spin. It can spin about an axis, and it can spin clockwise or counterclockwise. Yeah, it may spin fast. It may spin slow. Yeah, so you've got the magnitude of the angular velocity as well as the direction of the angular velocity. So what you said is actually correct. It is true that spin can be clockwise and counterclockwise, and but it can be at any rate. Yeah, you can speed up a top, you can slow down, and so on. Now let's come perhaps to the quantum context. So a quantum mechanical spin is can be thought of in a similar way. Yeah, it is not something that is spinning in our ordinary three-dimensional space. It is spinning in some internal space. Yeah, you can think of it that way. But many of the properties are very similar to that of angular momentum. And yeah, so but there are a few differences that one can highlight. Um, so first is that the magnitude of the spin angular momentum cannot take all possible values. It is it can take only certain values, um, and furthermore, the projection of the spin vector on an axis of your choice, you can choose any axis. So that will give you the component of the spin along that axis. That too cannot take arbitrary values. It can take only certain values. So you can say, but those values can be both positive as well as negative, and you know the details in the sense that the spin angular momentum can be an integer or a half odd integer, and the component along some direction can go from minus s to plus s in integer units. Yeah. So the main difference is that the possible spin projections are less. are quantized. So that is one main difference. And the second difference is that the square of the spin, which we usually write as s times s plus 1 h bar squared, that can't take all real values, unlike the spin of a top, which can take all real values, both positive and negative. Here it is restricted to those values for which s is a integer or half odd integer. Yeah. So, however, I mean, all is not lost. If the spin becomes very large, yeah, if S is large, then the behavior becomes rather classical, and this is the limit of large quantum numbers. So the fact that the spin takes only discrete values between plus s and minus s, or the spin projection, that list of values becomes larger and larger, and almost becomes continuous. Yeah. So this quantization is smoothed out, and you recover the classical freedom to point in any direction. Yeah. So you can certainly visualize it in a sense as a top that is spinning, but only along certain, but has only certain spin projections, at least roughly. Yeah, I don't know if that addresses your question. That was question of, you said, Megha, is it? Sorry, whose question is that?
Yes, sir, it was from Megha, who's also moderating the session.
Okay, fine. Yeah, I mean, I can say more, but if there is a specific question, that will guide me. Yeah, I mean, the theory of quantum mechanical spin is certainly built on the theory of classical angular momentum. And what one does is to abstract certain features of the classical angular momentum theory, in particular, certain group theoretic and Lie algebra type of properties. Yeah, in particular, that the Poisson brackets of Lx, Ly, and Lz have a certain relation among each other, Lx with Ly is Lz. That feature is retained in the quantum theory, and that really is the way to, in practice and through calculations, how one handles it. Okay, so you tell me if I have addressed your question to some extent or not.
Yes, so you have addressed. Now, as we have certain time limits, so let's move to second question now.
Okay, fine. Yeah.
Good evening, sir, and everyone. So the next question is asked by Simrandeep Kaur of MSc first year, and she asks that which is the most appropriate interpretation of quantum mechanics? Why is it the most coherent explanation of quantum phenomenon?
Okay, so the interpretation of quantum mechanics that I am most familiar with, and the one that we use in practice, is the one due to Born, originally due to Born. It is the probabilistic interpretation. Yeah, and I think you know what it means, what it says. So Born proposed that if you have a quantum mechanical state described by a wave function, psi, say in the position representation, where you have a psi of x or a position r, psi of r, then that psi is a probability amplitude, which means that the absolute square of psi times dx or dr, d cubed r, gives you the probability of finding the system in a configuration in a small volume dr around the point r. Yeah, so this is the most straightforward and commonly used interpretation of quantum mechanics. Of course, you're not obliged to work in position space. You could work with the momentum space. So you can talk about a wave function in the Fourier space, psi tilde of p, and then psi tilde of p absolute square times dp divided by 2 pi would be the probability of finding the particle between momentum p and p plus dp. Yeah. I mean, this is a very important idea, and so one would say that the interpretation that we are giving is a probabilistic one. It's a frequentist one. So in practice, what it means is that you deal with ensembles of systems, or you make the system, you make identical copies of the system. Yeah, all hydrogen atoms in the ground state, you prepare them, maybe 100 of them, and you make measurements, say, of the position of the electron in each of them. And the fact of the matter is that in every measurement on a different copy, you get different positions. This is a fact of matter, of nature. And we say that that has to do with quantum fluctuations. Now, I mean, it's just like saying that in a gas of molecules, if you measure the velocity of a molecule, depending on which molecule or when you do the measurement, you will get different answers. Some molecules are moving rightwards, some upwards, some southwest, some have larger velocities, some have lesser velocities. So we ascribe that to thermal fluctuations, and that is somewhat familiar to us. And the distribution of those velocities is goes back to Maxwell and Boltzmann. A corresponding thing is now happening in quantum theory as well. So we have a distribution of positions which is given by the absolute square of the wave function. This is the interpretation that we use. So if you make several measurements on several identical copies of the system, you will get different answers, different measurements. But if you plot a histogram of them, that histogram will approach, upon normalization, the shape of the square of the wave function. Yeah. Quantum mechanics does not predict what will happen with definiteness when you make one measurement. It will tell you the probability. When you make one measurement, you have a probability of finding the wave function or the position somewhere, but you may not get that. I mean, it will give you the probability. So it will not give a definite answer. There is an exception when the system is in an eigenstate of the observable you're measuring. In that case, with 100% certainty, you will get the value of the observable corresponding to that eigenvalue, corresponding to that eigenfunction. Yeah, so not everything is unknown. If you are an eigenstate of energy and you measure the energy, you will get the value of energy that's associated with that eigenstate. Yeah, there are other interpretations of quantum mechanics, but in practice, they are not something that I would suggest as the most appropriate. I think the question was, what is the most appropriate interpretation? I think this is the one. Yeah, we need to learn to live with it. Yeah, so quantum phenomena are intrinsically probabilistic, and just like thermal phenomena are. So this is not a new thing in physics. It has been with us for the last 200 years. We know that thermal fluctuations are present. It's just that there's a new source of fluctuations.
Alright, sir. So we'll move on to the next question. So the next question comes from Simrit. He's from MSc second year. He has asked that, in a way to have a theory of everything, which is the best way to lead general relativity or quantum gravity?
Okay, so all right. So okay, let me make some distinction here. General relativity is a classical theory. It's a theory of classical gravity. Now, our experience with other classical theories, such as electromagnetism or Newtonian mechanics, yeah, is that in certain domains, such as microscopic domains, quantum effects become important. So that we need to, in some sense, quantize these classical theories. So by analogy with that, we suspect that maybe because general relativity is a classical theory, there may be some domains, perhaps very small scales where gravity is important. Yeah, so far there are no real situations like that, but we suspect that maybe in situations where gravity is important and quantum mechanics is important, we will need to develop some quantum theory of gravity. Yeah. Yeah, so I mean, your question was which must lead the way or something like that. Yeah, so we are suggesting that I mean, okay, when I say we, this I'm just talking about the general feeling among physicists, and this is no by no means uniform feeling about among everybody, but a large fraction of people do have this view that. Mm, uh, so general relativity is only classical, and it might need to be replaced by some quantum version. However, this may not be the case. That right now, as far as we can tell, general relativity is only relevant at large scales. Yeah, I mean, solar system, galaxy, and clusters of galaxies and universe, and those domains, quantum mechanics is not at all relevant. Yeah, so you would have to find a regime where both quantum and gravitational phenomena are relevant, and this may be at the singularity of a black hole, or in the early universe, yeah, where we know that general relativity is not complete. Yeah, or at very high energies. Yeah, right now we are only at 10 to the 19 electron volts, but I mean at very high energies. Uh, um, yeah, so very high energies where Planckian energies, it could be that gravity is also important. Um, yeah, so I think, of course, it could be that quantum mechanics itself needs to be revised. There are some people who believe so, or have some ideas in that direction. But I would say that there are fewer people who have that view. Yeah. But how these two are to be combined is still very unclear. Yeah, so, and the problem is that we do not have access to experimental phenomena in such regimes. Yeah, we are at present only observing some big black holes in the center of a galaxy. These are not quantum in any sense. You would need some microscopic black hole to be able to look at gravitational effects. Yeah. So the other thing I would like to maybe point out is that, I mean, physics seeks to understand phenomena. Yeah. We try to build models of natural phenomena, of natural processes, and make predictions about them and manipulate them. Yeah, we want to manipulate systems, whether they be atomic systems or otherwise. Yeah. So now sometimes these attempts to build models leads to some bringing together of ideas. It was already explained that Newton combined terrestrial and celestial gravity, and that was a great step forward. Yeah, and same way Maxwell and Faraday were able to combine electric and magnetic phenomena in a common framework, and they were even related. So in sometimes some kind of unification or combining happens. It doesn't always happen that way. Yeah, the weak and electromagnetic interactions have been combined in a sense in a common framework, but they are actually they mix. I mean, it's more of a mixing than a unification. Uh, yeah. So what nature chooses to do, we don't know. I would and I would suggest that it's important to understand some phenomenon, some model, some thing. Uh, if it leads to and the history of physics has been that if you understand one system well, those ideas usually help to understand some other system. Maybe you did not even anticipate it. Yeah. So it's worth understanding individual systems or phenomena in detail. A direct attempt to find some kind of theory of everything has not panned out so far, at least. Yeah. So let me say it this way: a theory of something that describes some phenomena can be a stepping stone to a theory of some other things. Yeah, and this is a something to bear in mind. That is a way to actually find new theories or combine things by looking for a theory of something, understanding something well, rather than try to find a theory of everything.
I think that answers the question, sir. Thank you. So the next question will be asked by Sanskriti.
Okay.
Okay, sir. So the next question is from Armandeep of MSc 2. She asked that how does an electron know about which path to take in any wire or a field?
Um, how does the electron know which path to take in a wire on a field?
Wire or a
Uh,
field.
Okay, sure. Uh, yeah. Um, okay. So what can we do? We can observe and measure the behavior of electrons and try to build a model or a theory describing phenomena involving electrons. Now, one observation that we make in this process is that electrons do not behave like what we are more familiar with, like planets and cricket balls and so on. Electrons do not behave in a manner familiar to us from macroscopic phenomena. In particular, for most quantum phenomena, we cannot think of the electron as having a definite trajectory, yeah, where at each point in time it has a certain position and a momentum. Such a description is not feasible. Yeah. On the other hand, the probability for an electron to go from one initial position to some final position, we can tell about this probability. And the question is, what kind of answer do we find? It Now we can measure this and try to build models. And what those models tell us is that it is as though, please follow my words carefully. It is as though the electron is sampling every path between the initial position and the final position. Yeah, it is sampling every path. I'm not saying it is following every path. I just said there is no concept of trajectory of an electron, but it is as though the probability of finding it there is as though it has sampled every path, it has tried out every path, and the probability of reaching there is some kind of a sum or a combination of the amplitudes among of each of the paths. Yeah, there's some probability amplitude for each of the path, which we assign using the exponential of the action, I times action over h bar, to every path, and we need to combine these probability amplitudes to get the probability for the electron to go from here to there. Yeah, so this is what we infer from experiments and building models for them. Yeah. Now, so I mean, okay, there is one interesting limiting case, the classical limit. Yeah. Uh, where the action is rather large compared to Planck's constant. Yeah, when you're in macroscopic situations. In this case, it turns out that the probability amplitude for most paths simply cancel each other out, leaving basically one path, which is called the classical trajectory. Yeah. So in the classical limit, macroscopic limit, we do find that the electron seems to follow a definite trajectory. Yeah, but in the once you're in the quantum domain, there is no real single path. Yeah? It's a combination of paths. Yeah, as far as, I mean, the question that was asked was, how does the electron know which path to take? Yeah, see, we are not in a position to ask the electron, or yeah, what we can infer is make measurements of the position and find a probability distribution and see whether we can reproduce that as a sum over paths, and that does succeed. Yeah. So we don't I think the word path of least resistance was used. I would not quite use that. I would say the path that extremizes the action, for which the action is stationary, that is the dominant path in the classical limit. But once you go away from the classical limit, all paths are relevant, some more than the other, as weighted by the action. Yeah.
Okay, sir. Thank you.
Yeah.
Next question will be asked by Anshika. Anshika, you are unaudible.
Sorry, sorry. Uh, the next question is asked by Twinkle from MSc second year. Why is there no other spin than the integral multiple of half h bar?
Okay. Um, yeah. So, okay. So we talked a little bit about spin before. Um, uh, yeah. So let's try to. Um, okay. So what are the facts? Yes, it is true that in 3 dimensions, and this must be emphasized, in 3 dimensions. Yeah. Particles. Uh, have either spin 0, half, 1, 1.5, 2, and so on. Okay, and there are examples of particles of all of these sorts. Um, Now, and on the other hand, we do not find particles with spin which is intermediate between these values. Uh, yeah. Now, where did this come from? Um, and can it be violated, or can there be other possibilities? Yeah, both are interesting questions. So first I will tell you that there are places where this is violated. So in particular, there are systems that are purely two-dimensional. Yeah, these are called anionic systems. There are some special kind of particles that move only in two dimensions, but in the presence of a magnetic field and such like. Yeah, in such systems, it turns out that the spin need not be purely half integral. It can take continuous values. Yeah. So depending on the dimension, some new features may arise. That is worth noting. Um, and that is a very interesting possibility. Uh, the other question which you raised is that why is this the case? Yeah. Uh, all right. So, um, all right. One has to take time to answer this, but maybe I will. Okay. So where does this come from? As I was saying before, you have the model spin angular momentum by analogy with orbital angular momentum by postulating certain observables, which I we call Sx, Sy, Sz, which satisfy the angular momentum algebra. Now, the story of quantum theory is that you take the classical observables satisfying certain classical Poisson brackets and quantize the system. And what does quantization mean? It means representing these observables as matrices, Hermitian matrices, such that the commutators of those matrices matches the classical Poisson brackets up to some factor of I h bar. So this is the problem of finding a representation, yeah, of the classical Poisson brackets. This is what we have learned about quantum mechanics. And this is also what Schrodinger Heisenberg did. They took the XP Poisson bracket, X with P is 1, and quantized it, find a representation of that such that X hat with P hat is equal to I h bar times identity. And there is a way to do it. You choose P to be minus I h bar d by dx. If you choose it to be that differential operator and compute the Poisson, commutator with X, you will get I h bar times identity. We do the same thing with spin. We look for matrices, three matrices, Sx, Sy, Sz, such that the commutator of Sx with Sy is equal to IH bar Sz. Yeah, and it turns out that you can do this only in certain circumstances. You can do this only when the dimension of those matrices is certain values, and the value of the spin, which is given by the square of the spin angular momentum, s squared, sx squared plus sy squared plus sz squared, the only representations that are available, they must be unitary representations. Yeah. For the probability interpretation to be meaningful, it turns out that the only representations, unitary representations of this Lie algebra are labeled by an integer or a half odd integer. Yeah. So this may sound like a mathematical explanation, but this is actually how we handle it. Yeah. It is a matter of whether certain representations with continuous values of spin are available or not, and it turns out they are not available. And the proof of this you have even studied. You can develop the representation of spin using a vacuum state and raising and lowering operators, and you will see how only certain values come about using certain identities among the Sx, Sy, Sz. Yeah. This is one answer. One can try to give an answer that is closer to experimental observations and so on. Yeah, and in terms of atomic spectra, how spectral lines get split in a magnetic field, and that also gives a lot of similar indications. That is the Zeeman and Stichmiller effects, the presence of magnetic field couples to the magnetic moment or the spin angular momentum, and it turns out that the spectral lines split into multiplets, yeah, into two or three or four, or that's kind of multiplets, you don't get a continuous spectrum due to the spin interaction. Yeah, and this is an experimental signature of a similar phenomenon, I would suggest. Yeah, and in some ways, this is how it came about. Pauli suggested spin based on these observations. Yeah, so the interaction of spin with a magnetic field produces a multiplet of states, not a continuous spectrum. Yeah, so yeah, so that's also why the spin projection cannot take any value. um, yeah, anyway, it is really a matter from representation of a certain Lie algebra or group.
Okay, thank you, sir. So, shall we move on to the next question?
Sure, yeah.
So, it will be asked by Vanshika.
So you've already touched the concept of action. So the next question comes from Dipali. She's from MSc first year, and she is asking that why is action such an important concept in physics? I mean, it's not a directly measurable quantity, but it still holds a lot of importance in physics. So why is that?
Okay, good question. Yeah. Okay, so the original formulation of mechanics was due to Newton, and in that case, we described a trajectory as a solution of certain second order differential equation. Yeah. Now, Lagrange and Euler and others, Maupertuis and others, including Hamilton later on, realized that the same equations of Newton could be reformulated in a remarkable way, not as a solution of a differential equation, but as the condition for something to be extremal, something to be minimal, yeah, or maximal. That thing is the action. Yeah. So this has been an extremely fruitful idea in physics, to think of an equation as as an optimality condition, extremality condition, or some such thing. Yeah, the best or the worst or the least. Yeah. And I mean, and this appears elsewhere in science as well. Uh, yeah. So in any case, the point is that there is this alternative. You can formulate Newton's equation or Lagrange's equations as the conditions for the action to be extremal. And it extends also to the phase space formulation. Hamilton's canonical equations can also be formulated as a condition for a phase space action to be extremal. So these were the first reasons why the action is very important. They gave an alternative formulation. And variational principles are very important. Even if you cannot solve an equation exactly,
Hello?
you may be able to make a variational answer and put it into action and extremize it. So that gives an alternative way of solution also. In the quantum theory, this is very, very widely used, variational approaches.
बारे
Yeah. Okay.
हाँ
Now, another
इंटरफेसिंग
reason
जितना
why
होता है रीड
action
और
is
राइट
important,
वाले
or
ਹੁੰਦੇ ਆ ਨਾ
such action
चलेगा आवाज
principles, variational principles are
हाँ
important,
ਤੇ ਰੀਡ ਔਰ ਰਾਈਟ
the
ਵਾਲੀ ਜਿਹੜੀ
passage from
ਕਮਾਂਡਸ ਹੁੰਦੀਆਂ ਨੇ
classical mechanics to either
हाँ
statistical physics
हाँ
or to quantum
ਹਾਂ
physics,
ਹਾਂ ਉਹ ਠੀਕ ਹੈ
cannot go
ਉਹ
directly
ਇੰਟਰਫੇਸਿੰਗ ਦਾ
from
ਬਸ ਉਹਨਾਂ ਕਾ
Newton's
ਪੁੱਛਦੇ ਆ
equation in
ਤੇ
any
ਹੋਰ
simple way. We
ਇੰਟਰਪਟਸ ਬਾਰੇ
don't
ਪੁੱਛਦੇ ਕਿ
formulate
ਕਿੰਨੀ
quantum
ਤਰ੍ਹਾਂ ਦੇ
mechanics
ਇੰਟਰਪਟਸ
by
ਹੁੰਦੇ ਆ
quantizing
ਉਹਨਾਂ ਦੇ ਨਾਮ
simplification.
ਪੁੱਛਦੇ ਆ
It is not easy to do that.
ਹਾਂ ਬਸ
On
ਜ਼ਿਆਦਾ
the other
ਡਿਟੇਲ ਚ
hand,
ਤਾਂ ਨਹੀਂ ਜਾਂਦੇ ਇੰਟਰਪਟਸ ਤੋਂ ਤਾਂ
both how
ਬਸ
it was discovered and how
ਹੋਰ
we
ਹਾਂ
discuss
ਇੰਟਰਪਟਸ
it
ਕੋ ਪੁੱਛਦੇ ਕਿ
today,
ਪ੍ਰਾਇੋਰਟੀ
the
ਕਿਹੜੀ ਹੁੰਦੀ ਹੈ
method
ਲਾਈਕ
of
ਜਿਵੇਂ ਟ੍ਰੈਪ ਵਾਲਾ
passing
ਫਸਟ
to
ਤੇ
the
ਆਂਦਾ
quantum
ਹੈ ਨਾ
theory or to the statistical theory
ਹਾਂ ਥੋੜੀ ਜੀ ਪ੍ਰਾਇੋਰਟੀ
involves
ਬਾਰੇ
the
ਪੁੱਛਦੇ ਆ
Hamiltonian. It involves the
ਹੋਰ
action. It
ਤਾਂ
involves the
ਬਸ ਇੰਨਾ ਹੀ
Lagrangian.
ਪੁੱਛਦੇ ਆ ਇੰਟਰਪਟਸ ਤੋਂ ਤਾਂ
I was just saying
ਹੋਰ
earlier,
ਬੇਸਿਕ 8085
the
ਬਾਰੇ
amplitude of a path in the quantum theory is given by the exponential of the action of that
ਯਾਰ
trajectory.
ਉਹਨਾਂ ਨੂੰ ਤਾਂ
It's
ਪਹਿਲਾਂ
not
ਸਰ
given
ਨੇ
by something
ਇੰਟਰਪਟਸ ਦਾ
coming out of
ਪੁੱਛਿਆ ਕਿ
Newton's
ਕਿੰਨੀ
equation
ਨਹੀਂ ਉਸ ਨੇ
directly.
ਪੁੱਛਿਆ ਨਹੀਂ ਸੋ ਮੇਘਾ ਨੇ
So,
ਖੁਦ ਸਾਹਮਣੇ
so
ਬੋਲਿਆ ਸੀਗਾ ਕਿ ਸਰ ਇੰਟਰਪਟਸ ਹੁੰਦੇ ਆ ਤਾਂ ਸਰ ਕਹਿੰਦੇ ਹੁਣ ਜੇ
great
ਬੋਲਿਆ ਇਹ
reason
ਨਾਮ
to
ਤਾਂ ਫਿਰ ਉਹਦੇ
pay
ਕਿੰਨੀ ਟਾਈਪਸ
attention
ਜਾਂਦੇ
to the
ਦੱਸ ਦਿਓ
action is
ਠੀਕ ਹੈ
that
ਉਹ
the
ਤੇ ਫਿਰ ਸਰ ਨੇ
action
ਉਹਨਾਂ ਤੋਂ
gives
ਇੰਟਰਫੇਸਿੰਗ
you
ਪੁੱਛੀ ਸੀ ਜੋ ਸਰ ਨੇ
paves
ਮੈਨੂੰ
the
ਕਿਹਾ ਸੀ ਕਿ
way
ਮਤਲਬ ਮੈਂ ਨਹੀਂ
to
ਦੱਸਣੀ ਉਹ
the
ਦੱਸਣਗੇ
generalization
ਇੰਟਰਪਟਸ
from
ਦੀ ਇੰਟਰਫੇਸਿੰਗ
classical to
ਵਗੈਰਾ ਜਿਵੇਂ
quantum
ਆਈਓ
or
ਰੀਡ ਬਾਰ
classical
ਵਾਲੇ
to
ਜਿਹੜੇ ਆ ਉਹ
statistical
ਨਾ ਇੱਕ
physics.
ਡਾਇਗਰਾਮ ਹੁੰਦੀ ਨਾ
Whereas
ਉਹ
the direct
1001
quantization of
ਵਾਲੀ
Newton's equation
S0
is
S1
not so
ਜਿੱਥੇ ਚਿਪ
easy to
ਸਿਲੈਕਟ
handle.
ਕਰਦੇ ਹੁੰਦੇ ਆਪਾਂ
Yeah, so this is why the action
ਹੈ ਨਾ
is very
ਉਹ
important.
ਵਾਲੀ ਡਾਇਗਰਾਮ ਸਰ ਚਾਹ ਰਹੇ ਸੀਗੇ ਉਹ ਨਹੀਂ
Yeah,
ਬੋਲੀ ਸੀ ਉਹਨਾਂ ਨੇ ਬਟ
yeah,
ਕਿਉਂਕਿ ਤੁਹਾਨੂੰ
but we
ਕਰਾਈ
may
ਨਹੀਂ
say
ਸੀ ਉਸ
it's an
ਟਾਈਮ ਤੇ
auxiliary
ਪਰ ਸਰ
concept.
ਉਹ
It is
ਸੁਣਨਾ
not
ਚਾਹ ਰਹੇ
something
ਸੀਗੇ
being measured
ਤਾਂ ਅਗਰ
directly.
ਤੁਹਾਨੂੰ
To some extent, it's true. Yeah. By the way, the action is also gives you an approach
ਹਾਂ
to
ਹਾਂ ਇੰਟਰਫੇਸਿੰਗ ਦੇ ਵਿੱਚ ਹੀ ਆਂਦਾ ਹੈ ਉਹ ਵਾਲੀ ਹਾਂ ਹਾਂ ਹੈ ਜਿਸ ਚ ਗੇਟਸ ਬੰਦ ਹੁੰਦੇ ਆ ਹਾਂ ਹਾਂ ਉਹ ਵਾਲੀ ਠੀਕ ਹੈ ਨੈਂਡ ਗੇਟ ਬੰਦ ਹੁੰਦਾ ਉਹ ਵਾਲੀ ਹੋਰ ਕਿਸੇ ਨੇ ਸੀ ਸਰ ਉਹਨਾਂ ਤੋਂ ਬਸ ਹੋਰ ਕੋਡਸ ਬਾਰੇ ਪੁੱਛਦੇ ਕਿ ਕੋਡਸ ਪਤਾ ਹੈ ਨਾ ਕਿ ਕੀ ਹੋ ਰਿਹਾ ਹੈ ਲਾਈਕ ਕੋਡ ਦੇ ਅੰਦਰ ਕੀ ਚੱਲ ਰਿਹਾ ਹੈ ਉਹ ਸਭ ਪੁੱਛਿਆ ਸੀਗਾ ਮਤਲਬ ਪੁੱਛਿਆ ਨਹੀਂ ਬਸ ਐਵੇਂ ਮਤਲਬ ਦੇਖਿਆ ਸੀ ਕਿ ਪਤਾ ਹੈ ਨਾ ਬਸ ਹੋਰ ਤਾਂ ਇੰਨਾ ਨਹੀਂ ਪੁੱਛਿਆ ਸੀਗਾ ਬਸ ਇਹੀ ਸਭ ਪੁੱਛਿਆ ਸੀਗਾ ਇਹ 'ਚ ਹੀ ਮਤਲਬ ਉਹ ਅੜ ਗਏ ਸੀ ਨਾ ਫਿਰ ਬਸ ਫਿਰ ਸਰ ਉੱਥੇ ਉਹ ਹੋ ਗਏ ਕਿ ਰੁਕ ਗਏ ਮਤਲਬ ਹਾਂ ਨਿਵੇਦੀ ਦੇ ਨਾਲ ਹਰਮਨ ਹੁੰਦਾ ਹੈ ਹੁਣ ਉਹਨੇ ਦਿੱਤਾ ਹੈ ਤਾਂ ਨਹੀਂ ਮੈਂ ਪੁੱਛ ਸਕਦੀ ਹਾਂ ਤਾਂ ਨਿਵੇਦੀ ਤੋਂ ਇਦਾਂ ਕੋਈ ਚੱਕਰ ਨਹੀਂ ਹੈ ਪੁੱਛ ਦਿੰਦੀ ਨਿਵੇਦੀ ਨੂੰ ਕੀ ਸਰ ਨੇ ਮਤਲਬ ਹਰਮਨ ਨੂੰ ਜਿਵੇਂ ਫਿਜ਼ਿਕਸ ਦਾ ਤਾਂ ਕੀ ਕੁਐਸਚਨ ਪੁੱਛੇ ਸੀ ਉਹ ਪੁੱਛ ਦਿੰਦੀ ਹੋਰ ਵੈਸੇ ਹਾਂ ਉਹੀ ਮੇਨ ਉਹੀ ਹੈ ਨਾ ਕਿ ਮਤਲਬ ਸਰ ਨੇ ਜ਼ਿਆਦਾ ਪੁੱਛੇ ਵੀ ਨਹੀਂ ਉਹਨੇ ਤੋਂ ਉਸ ਲੈਵਲ ਦੇ ਯਾਰ ਹੋਰ ਤਾਂ ਫਿਜ਼ਿਕਸ ਚੋਂ ਨਿਤਿਨ ਉਹਨਾਂ ਨੇ ਦੇਣਾ ਅਗਰ ਉਹਨਾਂ ਨੇ ਵਾਈਵਾ ਦਿੱਤਾ ਹੋਵੇ ਤਾਂ ਪੁੱਛ ਲੈਂਦੇ ਅਗਰ ਉਹਨਾਂ ਨੇ ਹਾਲੇ ਤੱਕ ਦਿੱਤਾ ਕਿ ਨਹੀਂ ਦਿੱਤਾ ਅਗਰ ਨਹੀਂ ਦਿੱਤਾ ਜਾਂ ਅਗਰ ਦਿੱਤਾ ਹੈ ਤਾਂ ਉਹਨਾਂ ਨੂੰ ਪੁੱਛੋ ਉਹਨੇ ਸਰ ਨੇ ਕੁਐਸਚਨ ਹੋਰ ਤਾਂ ਕੋਈ ਨਹੀਂ ਹੈ ਫਿਜ਼ਿਕਸ ਵਾਲੇ ਪੁੱਛ ਲੈਂਦੀ ਨਿਤਿਨ ਉਹਨਾਂ ਨੂੰ ਠੀਕ ਹੈ ਠੀਕ ਹੈ ਓਕੇ
Yeah, I mean, nature seems to like extremization principles, whether it is extremal surfaces or soap bubbles, or yeah. So these optimization problems come up very widely in science. So it's nice that we can reformulate Newton's equation also as an optimization problem.
Okay, sir. Thank you, sir. I think that answers her question. So moving on to Sanskriti.
So, sir, the next question is from Muskan Sharif of MSc first year. So it's a question like everybody among us is thinking these days. Like, what are the current emerging areas in physics?
Okay. Yeah, I mean, there are a lot of areas. Yeah, so let's preface this by saying that there are interesting developments and open questions and challenges in many areas of physics. Yeah, they are not restricted to any one area, and practically any area of physics you take will have some interesting developments going on. But how will you find out? How will you find the answer to your question? Of course, you have asked me, so I have to give some answer. But if you had to find out yourself, how would you do it? One way to do it is to you go look up what some of the recent Nobel Prizes have been. So that will give you an indication of some of the areas where developments have happened. Of course, it might take a while. There may be a time lag between a Nobel Prize and the development. But even aside from that, it does give you an indication of some of, I mean, not just a Nobel Prize. You can look at other prizes like various, even the Infosys Awards and the Wolf Prize, American Physical Society Awards. So all of these they serve to highlight certain areas or developments. And so that will be a good way to find out. Yeah. Another way to find out is to read some science journals, Scientific American or Resonance, or they usually have general articles on interesting areas. That will be a good way to find out. And there are also another thing. There are various lists of open problems. Right? Every so often, somebody makes up a list. Some experienced scientists, around the turn of the millennium, we had a bunch of problems by the Clay Institute. You would have heard two of them are in physics. One is in hydrodynamics, the other is in quantum field theory. But there are other such lists of open problems. So this is also an indication. Another thing comes from new technologies. Yeah, so new technologies or new theoretical tools. Both of them can facilitate development. So if there's a new technology, it will indicate that some new things are possible. So as far as specific areas, I'm sure you would have heard of many of the areas. I can mention a few. I'll probably miss out a lot. Yeah, so I mean, there have been new technological or technical developments, for instance, in interferometry. Yeah. Which have improved their sensitivity tremendously over the last couple of decades. So this has opened the window into gravitational wave astronomy. Yeah. And now we can even measure neutrinos, detect neutrinos reasonably well. So neutrinos can be used as another tool to do astrophysics, in addition to particle physics. Yeah. So one talks about multi-messenger astronomy, both gravitational and gravitational wave and neutrinos, as well as light in various wavelengths, infrared, etc. Yeah. So that is certainly one area. Another area that has developed and is in quite in the news is the entire area of quantum information and quantum computing. Yeah, quantum entanglement. So here again, it is driven by two things. One, the recognition that entanglement is a very interesting topic, theoretically speaking. A lot of developments have happened there, and also on the experimental side, it's been possible to manipulate quantum systems at microscopic scales quite well. So that has brought together both technological and theoretical development. So this is another fertile area that is seeing a lot of development. There are several other things I can mention. So, I mean, there are much older problems. For instance, the behavior of fluid systems, yeah, whether plasmas or neutral fluids, they show a myriad variety of phenomena, some of which are turbulence, or if you look at plasmas, there is the open question of using controlled nuclear fusion to as a power generating mechanism, and this is called magnetic confinement fusion. So that is the subject of tokamaks, where you use magnetic fields to confine a plasma and try to have a nuclear fusion reaction, deuterium tritium. So that is another area where there is a lot of work going on. But even on the theoretical side, understanding fluid turbulence or instabilities in fluid systems is an old problem, but much of it is not solved. So there are potential developments over there too. I did mention a little bit about quantum field theory and particle physics. So there too, there are many open issues. I mean, we have the standard model, but there are at least two areas where on the other hand, on the one hand, we have a theory, but we cannot solve the theory. We cannot predict the mass of the proton. We cannot tell many things about strongly interacting particles. So there is need for studies over there. Yeah, these are challenging problems, but open problems. And on the other hand, there are experiments going on at CERN and elsewhere where we scatter particles. A lot of importance in understanding how to calculate scattering cross sections in efficient ways, and there have been lots of developments in developing more efficient ways than summing Feynman diagrams. Yeah, maybe because there are a lot of diagrams, and there are more efficient ways. So how to calculate scattering amplitudes in more efficient ways. So a lot of new developments are happening in that theoretical area. There are, if you go towards condensed matter physics, there are many things. There are quantum materials with very novel features. A lot of efforts are going in that direction. Quantum materials, yeah. Phenomena like novel states of matter, high temperature superconductivity, fractional quantum Hall effects, and a whole variety of novel behaviors are being seen in strongly correlated electron systems, or topological features that arise in condensed matter systems. So this is a very active area of research as well as technological development. So that is yet another area I can mention. Another area is, you could say, the area of chaotic dynamics, both classical and quantum chaos. There are many open questions which are there, and computer simulations have really opened up that area, so that one can explore phenomena through computer simulations and then try to understand them in a deeper way or in a theoretical way. So the area of nonlinear dynamics, complex systems, you may hear of things like synchronization and so on. So this is another area. Uh, um, yeah, of course, there is space exploration, building satellites, launching and controlling satellites. Yeah, so this is very much active area where we have ISRO is also very much involved. Um, let's not forget other areas. I mean, I mentioned fluid turbulence, but there's another part of it, which is weather prediction or climate science. This is also extremely important area from practical point of view and from the theoretical point of view. Having a clear, good understanding of atmospheric physics and weather prediction, as you can see, will be very, very useful. It is a challenging area, or even understanding the monsoon in a better way is relevant to us. Or for that matter, climate change. Yeah. So this is yet another area of active development. Climate science, if you call it that. Low temperature physics is, of course, it's been around for a long time, and it continues to be important. What happens to systems at low temperatures? So just as you want to go to high energy, you want to go to low temperatures. There are always surprises over there. Bose-Einstein condensates and condensates of other things, fermions as well. Yeah, and using those condensates as analog, as models, as way of simulating other systems. Yeah. There are a lot of theoretical models you can make up, but it turns out you can actually simulate them using atomic gases and low temperature systems. So it's very interesting from that point of view. There are other theoretical areas like the search for theories of quantum gravity and string theory. This is another area of active research. So I mean, I'm mentioning things which come to mind, but I'm sure I've missed out others. Of course, there's the entire area of machine learning and artificial intelligence. So that's another area where new techniques are coming up. Um, uh, yeah, so you can add if you have heard of other things. Yeah.
Thank you, sir. You gave a lot of things to search about.
Physics is also very important.
I'm sorry, I did not hear what.
Nuclear physics, particularly.
Oh, of course. Yeah. Yes, nuclear physics. So, I mean, I did mention particle physics, but certainly nuclei. Every so often we hear that there are new types of nuclei, very heavy nuclei discovered, which have peculiar properties. Yes, indeed. And nuclear physics is a difficult subject. It is very difficult because it's a strongly interacting system and many body system, and it is not possible to somehow solve quantum chromodynamics and understand nuclei. That doesn't work. So you need effective models of nuclei, and there are many very interesting ideas in those areas. So we can add that to the list. Optics I didn't mention, perhaps I didn't, but perhaps, I mean, optics is in connection with quantum entanglement. Often you use optical systems to model such things. As well as other areas. I mean, nanoscience and nanomaterials are also very important. If you want to build a quantum computer, you need to know lithography. You need to have set up Josephson junction circuits to set up a qubit. So lithography is important in that. So material science is how you actually build materials. So we have to bear that in mind.
Let's move to another question.
Thank you.
So there's an interesting question from Shashwat Giri of BSc third year. He asks, what exactly is vacuum? Is it really an empty space or just a relative term? Also, gravitational fields and lots of other unknown fields still work under vacuum, and this contradicts the same. Need a clear cut clarification about complete emptiness.
Okay, so this is about the vacuum. All right, so I think maybe to start addressing this question, it is good to think about how do you create a vacuum. Yeah, so how do you create a vacuum? Well, what you do is you start by making a box and start sucking out the air from it. Yeah, you suck out the air, you suck out one of the charged particles you can find. Yeah, and any other matter. If there is some dust inside, you want to remove that as well. And if there's a book inside, you want to remove that as well. Yeah, so that's how you start making a vacuum. Yeah, so that's what a vacuum is in practice. And now you can start asking about its properties. Having created what you believe to be a vacuum, what are its properties? So when I say properties, I mean, okay, you try to send a sound wave through that vacuum. Yeah, you speak on one side and ask whether you hear it from the other side. It turns out you can't hear properly, unlike in air. So sound doesn't propagate in a vacuum. Similarly, you can try to heat one side of that box and see whether you get the heat on the other side, and turns out you don't. So heat also doesn't propagate in a vacuum. So so we're beginning to see some properties of the vacuum that you have just created. On the other hand, you can try to send an electromagnetic wave through the vacuum. Yeah, you can shine a light and see whether you see it on the other end through some detector or your eyes. It turns out you do see it. Yeah, so there are some things that can propagate through what you thought was a vacuum, and there are some things that cannot propagate. Yeah. Um, so on the one hand, sound required atoms to move around, yeah, and propagate a wave, and so also for heat you needed the random thermal motion of atoms and molecules, whereas for the propagation of electromagnetic field you don't need any atoms present. Yeah. So yeah. um, yeah, so it is empty space, but that empty space is able to support certain phenomena. um, okay, so I've tried to convey a couple of things. Now we can pursue a little further. Suppose I said you shine a light through a vacuum. Now suppose you shine a very strong electric field, yeah, very strong electric field, apply. Then it turns out that some even more remarkable things start happening. If the electric field is sufficiently strong, you can polarize the vacuum in the sense that electron positron pairs can be produced and fly out, and then you can detect them. Okay, so a vacuum has this interesting probable possibility of being polarized. When I say polarized, I mean some sort of separation between charges, positive and negative, in this case particle and antiparticle, which can then be detected. So I mean, you could ask whether those particles were already present in the vacuum or whether or not. Yeah. So of course, you had tried to remove the charged particles, so presumably they were not present. But it is the effect of this strong electric field that has produced them. Okay, so the vacuum has the possibility to germinate new particles. Yeah. Yeah, so it is not a completely inert medium. um, yeah, so this is one additional feature that I would like to point out. um, Let me try to give some more points of view on the vacuum. um, okay, what we believe to be the vacuum, the space around us, if you even if you suck out all the air and don't apply strong electric fields, it turns out that we have, in the last decade and more, we have found that that vacuum has a condensate of a certain field called a scalar field. This is the so-called Higgs vacuum condensate. Throughout the space around us, there is a non-zero vacuum value of the scalar field. It is 246 GeV. It has been measured. It is there everywhere around us. You cannot wish it away, and that is very important to give masses to particles and so on. Right? So this, what we thought was a vacuum, is not completely empty. It has got this Higgs scalar field permeating throughout, but at a constant value. All right, so that is yet another feature of this vacuum. It has other features. There is something called the Casimir effect that one can look up. Yeah, that is having to do with the properties of the vacuum. Um, Let me perhaps maybe let me take one different point of view. What how to think about the vacuum? Yeah, see, when we study a quantum system, oftentimes we develop it in the second quantized framework with a many body system. We develop some creation annihilation operators for the particles, but we start and we build up a certain Fock space, a Hilbert space for the many body system. How do we build it? We start with the so-called Fock vacuum. That Fock vacuum is the state which is annihilated by all the annihilation operators or lowering operators. So if you want to think what is the vacuum, it is that state where there are none of those particles. Yeah. And then we create the Fock states by applying the creation operators. Yeah, so this is another way to think about the vacuum in the context of quantum field theory or many body physics. Yeah. It is the state which is annihilated by which is made to become zero by applying the annihilation operator. Let me also mention the vacuum in the context of the Dirac theory. See, in the Dirac's theory, uh, I mean, in a simple-minded approach that he originally had, he said that we think of the vacuum as one in which all the negative energy states are filled and the positive energy states are empty. Now, this is a somewhat not very accurate way of speaking. One has to talk about it in the field theoretic context. Yeah, but roughly it is not a wrong idea. There is a sense in which then sort of the negative momentum states are all filled, yeah, and the positive ones are empty. And if you hit this vacuum, that is, you send a very strong electric field or you do other such things, then it can excite. It can create an excitation of that vacuum, which may look like an electron-positron pair in the context of the Dirac theory. So, or in the Dirac language, you create a hole in the negative energy C. Yeah, so the vacuum has zero energy, but by suitably shaking it or shining a light or doing other such things, you can generate particles, and there are phenomena associated with that vacuum. Yeah, so I mean, I said different things about the vacuum. I hope this sheds some light. Um, I don't know how clear cut it is. I know this person asked about clear cut. Yeah, but these are some of the issues that one has to understand when understanding the vacuum. Yeah, a vacuum can have energy. That is in gravity. Yeah, in gravity, the vacuum can have energy. This is called, anyway, that's yet another feature. But even in quantum field theory, in particle physics, vacuum can have a scalar field present in it, a constant scalar field. This is not in dispute. This has been measured. It is very much there. Yeah.
Okay, thank you, sir. Now we'll move on to the next question, which will be asked by Vanshika.
So this will be the last question of our round. This question is about machine learning and AI, and how is it relevant in physics? Like, why do we need to do it currently in this time of
Okay.
physics?
Um okay. Yeah. Let's see. Maybe to get some perspective, let's say that, see, physics is a fairly mature subject in the sense that it has been around for some time. I mean, even from Newton's time, more than 1687. So yeah, so more than 350 years, 350 years or so. In the history of physics, machine learning and artificial intelligence are relatively new developments. So I would say that they join many other old and new tools which we have at our disposal, which have been developed over the years. They have been there. These machine learning and AI are beginning to have some impact, um, though it is not very widespread yet. Uh, um, I mean, of course, there are certain areas where it may be more useful or more early useful at an earlier stage, especially areas where there's a lot of data which you need to sift through, or you have some sort of search problems where you have some energy surface that has got a lot of very, very uh, nearly degenerate minima, and you need to search through all of them. Other search problems where you're searching for some optimal path among a large number of paths. Um, and in this context, machine learning can be quite helpful. Yeah. Uh, yeah. Now now, physicists have also contributed to the development of machine learning. In fact, this year's Nobel Prize, yeah, Hinton and another person, Hopfield, they have used physics ideas, Boltzmann machines, and such things to develop machine learning algorithms and tools. Yeah, so physicists are contributing to machine learning. Yeah. Machine learning has also been useful in physics. For instance, I did mention search problems, or yeah, they've also been useful in materials physics, where we are searching for materials with specific properties. Yeah, and rather than make each of those material and check its property, it may be possible to use some kind of simulation and a way of artificially checking or simulating new materials and checking their properties. Yeah, so that is another place where it has had an impact. Um, yeah, and also in chemistry. In fact, this year's Nobel Prize in chemistry also has to do with machine learning, artificial intelligence areas. Yeah. However, I would like to also say that it's good to see what happened to other new technologies, how they were developed. Yeah, I mean, this is not the only new technology. Even in our own lifetime, internet or computers have come as new technologies, and they have revolutionized science and physics. They have played an important role. Uh, or for that matter, even earlier things like the invention of the steam engine really opened the gates to understanding thermodynamics, phase transition, critical point, critical opalescence, yeah, Tyndall effect. All these things came up because of a new technological development, namely the development of a steam engine. Yeah, so similarly, I would expect that developments in machine learning will lead to new developments in physics, and conversely, they will be physics will able to improve those machine learning algorithms or ideas. Uh, and However, I would also like to say that, see, even based on this history, it is not as though the machines are going to lead us somewhere or lead us, yeah, or we are going to be replaced by them. Uh, um, yeah, I mean, we have not been replaced by computers. We take the help of computers to do certain things, like have a seminar sitting in Chennai, some people in, yeah, in Chandigarh, or for communication and numerical simulations and all these things. Yeah, but we are still deciding what the computer should do, and we are giving it its algorithm, and we are checking the output, and so we need to be very critical about that. Yeah, yeah, we can of course be misled by computers. We may allow ourselves to be misled by computers, that is uncritically taking some computer output and wrongly interpreting it as the reality. Yeah, so the same thing can happen in artificial intelligence, where we wrongly uncritically accept some output from some large language model as the truth, and get misled. So we need to be careful about that. We need to have checks of whatever these things are saying through order of magnitude estimates, other techniques, etc. Yeah? And physical intuition. There is no replacement for that. Um, so it's a new set of tools. And on the other hand, humans as scientists can try to understand why those techniques work. See, we have developed some large language model and some machine learning, but it is largely some trial and error. Something works. We don't understand very well why those methods work, and I think some effort will go into understanding why those methods work, or to what extent they can work. Yeah. And of course, the exploitation is another part. We want to exploit them to solve societal problems and physics problems. So that is another thing. Yeah, I mean, just now I heard Nandan Lilekani and others saying that we should not try to develop yet another large language model. We should use the ones that are developed by to use its language, the big boys of Silicon Valley, and but use it to solve some problems which are of relevance to us. Um, yeah. Uh, yeah. So I think we should see artificial intelligence and machine learning in that context. It is not artificial intelligence. It is some kind of help that we can use machines to do for us. It is not some independent intelligence, I think. Of course, it can have bad consequences, just like anything else, which we have to guard against. Uh, yeah, I should also point that this machine learning and artificial learning can be useful in other purposes. It can be useful in the learning process, in the education process. Yeah. So now you can query Google about some topic, and it is able to put together a summary of that topic, and that's very helpful. Of course, you have to check it against the sources. So it's helpful in that process. I think that is certainly a place where you and I are already using it. um, yeah, these chatbots and so on. Um, um, they're also very useful in suggesting computer code. Yeah, if I don't know how to say write a C++ code to solve a certain problem, one can ask this large language model, and we propose a code. We will have to just test it and calibrate it and change it. Or if you don't know Mathematica, you might ask it to give a Mathematica code to plot a certain figure in a certain coordinate system, and it will help you do that. So I think it's very useful in that way. Yeah, to do programming and such things. So sure, please learn how to use it and make use of it in whichever context, solving physics problems, learning, or improving the model itself. Yeah, so it's here to stay. Yeah.
Okay, sir. Thank you for this question. Vanshika is just disconnected because of the battery drainage of her laptop. So before starting second round of questions, that is random question now, I would like to ask you if you want a break of 2 minutes, or shall we continue with the session right now?
Um, okay, maybe a break of 2 minutes is a good idea, perhaps also for you. Um,
Okay,
so it's now 7:23. So when does 2 minutes end? Uh,
okay, sure.
okay, yeah. We'll restart in a couple of minutes, 7:25 or 26. Sure. Okay.
Good evening, everybody.
Good evening, sir.